All right, welcome back to the online causal inference seminar. Today we're excited to have Jakob Runge from the University of Potsdam, who will talk about the Python package, causal inference on time series data with a Tigramite package. Questions today will be handled by Razi. So Razi.
Thanks, Dominic. Per usual, please ask your questions using the Q&A box. I'll try to raise them if they're quick clarifying questions. Otherwise, I'll leave them to the end. And without further ado, Jakob, please take it away.
Thanks. Go ahead. All right. You should see my slide. So the goal of this is to present an overview of the Tigramite Python package for causal inference on time series data, which is maybe what sets it apart. And I'll go a little bit into also like an overview of how I intend this to be used by practitioners, and then also under the hood what the functionality is, and potentially also about some more methodology that is implemented there. All right. So without further ado, my motivation that guided me in my research journey was really research about causal inference on complex dynamical systems. And this is mostly Earth system data that I dealt with in my path. And there you would have questions like what drives flood events, and questions of causality arise there, like what causes extreme events, for example. And this can be different parts of causal inference. This is partially like the tipping points that are in everyone's mouth now, like how do they develop and how can we detect which systems are tipping? There's a lot of things that can be done also with causal inference. At least I try to push that statistical framework into that community, which is not so aware of it. Another thing is like improving climate models using what is called hybrid modeling, like using statistical models inside that runs just faster, and thereby trying to get the uncertainty or this warming trend to like a smaller uncertainty range. And then also something like teleconnection networks. So these are emergent phenomena in the climate system, and they are spatio-temporal phenomena, and that also guides a lot of my research, how to deal with spatio-temporal data when you are interested in causal inference of these systems. So I used a workshop some years ago where I tried to aggregate what the challenges of complex dynamical systems data are for causal inference, and that has led to this perspective paper in 2019. And yeah, the challenges are, for example, at the process level, like the underlying level, like the system might be highly autocorrelated, have time delays, non-linear, chaotic. The weather is, as you know, there's different time scales, a slow ocean, fast atmospheric dynamics. The noise distributions might be extreme. And then at the data level, we have often the issue of the data is basically spatio-temporal from satellites, while we want to just have a node and the data belong to that node in our graph. And that might be a problem for like defining your variable at the outset. We have then problems of unobserved variables, hidden variables, time subsampling when the satellite traverses a region only every few days, measurement errors, selection bias, these problems maybe from many other fields. Discrete data, categorical data can also be a type of data in this range, and dating uncertainties in paleo data next to the standard statistical challenges of like sample size, high dimensionality, and so on. So my group's work was trying to like develop time series causal discovery, and recently also causal effect estimation methods for this. And so a typical object here is not this graph that you might typically have, but we deal with time series graphs. So these are stationary. If you assume a stationary system underneath, would look like this, and they are infinite in time. So you would repeat this structure for every other time lag here. And this means that this graph in principle is an infinite graph, and this is quite an interesting thing actually, also from causal inference perspective. And we had some work of projecting stationary infinite graphs to finite graphs that is currently in the archive. I didn't put the reference here. And another way to represent these systems is in such process graphs, also a field or summary graphs, sometimes they are called, where for example, would have a cycle in this case, where the time series graph does not have a cycle because the cyclic relations are resolved in time. So this is the object that I looked at mostly. And the way we dealt with this is by this range of causal discovery methods that I somehow called PCMCI at some stage, relating to the PC algorithm, and the momentary conditional independence tests, which tries to make conditional independence testing valid and well calibrated for time series data. And the methods we have here cover a range of assumptions from like PCMCI plus, allowing for instantaneous relations. Then we have like LPCMCI that learns latent time series max. Another option is JPCMCI, which tries to move into this joint causal inference framework, where you assume that you have multiple data sets from multiple different environments. And this is illustrated here. We would have like x1, x2 as the system variables, we call them. And then you can add these context variables in the graph, in the time series graph in this case. And they can be time dependent and basically cause each environment, or they can be also static for each data set. And then you have such a contextual space node. And in the end, even though that sounds complex, you can still learn a graph that then covers system variables as well as context variables. And this allows to also overcome some types of hidden confounding due to these contexts. Maybe people know fixed effects panel regression, and this is trying to do that in a causal discovery framework. And finally, a method here that tries to deal with non-stationary data. So we call this causal regimes, and they may change over time, and you don't know which time sample belongs to which time point. And so this regime PCMCI tries to learn both the different graphs and the samples at which these occur. And this is really just an overview here. There's maybe some time to answer questions on these methods. And another research avenue we developed in the group is now effect estimation, on the one hand, just for like IID settings, and then also for time series graphs. Okay, I mentioned that I a little bit target this talk also to practitioners as an overview, and maybe that slide is more for those. I wrote a review or a guide paper 2 years ago with colleagues that tries to really illustrate just a whole framework of causal inference for time series methods, and also tries to give a little bit of like a bird's eye perspective. So covering foundations and a method overview, and then also a method guide, and worked through case studies. And I would like to share one of those bird eye views now. So you might have heard of Pearl's causal hierarchy, and I kind of like this concept of making the different questions that researchers have and structuring them so they learn which methods are suitable for their task. So you assume some underlying system, and then a user may have a question, and that may be a non-causal question. It may be a qualitative question about causality, or quantitative, so meaning causal discovery or causal effect estimation, or a counterfactual question. And then they have assumptions about this system, and they have data about the system. This might be observational or interventional. And this gives then rise to what Pearl and maybe Elias framed as the causal inference engine. And just opening up this space of assumptions here and space of variables. So the variables I mentioned already are often not that easily set in stone in complex spatiotemporal systems. So you first have to define variables, and there might, for example, be two basically underlying time series, and so it's a two-dimensional underlying node, or it might be a node that extends into the past, so it's like a longer past, a delay vector. You might have a full spatiotemporal setting here and different types of data. And the assumptions, I try to kind of put that in a little picture here, you can make about the system are in causal effect estimation, the whole graph, and that may have latent variables, and there might be context, multiple environments, and delays. Or in causal discovery, you might assume whether the graph has hidden variables or even cyclic relations. There's lots of research recently for cyclic causal discovery. And you might have assumptions about the functional form and noise distributions that might lead to methods like Lingam or so on, and observational noise and stationarity in the time series context. And given like a reflection about these questions that the user has, the assumptions they are willing to make, and the data they have at hand, I have this huge flowchart that I try to give them as a kind of recommendation system. So they would, for example, start here, and then the first thing is, do they have a causal question? And that's maybe in the last slide, is it something about just predicting in distribution or so? Then it's not a causal question. If they are, however, have a causal question, then first thing is maybe, are their causal nodes defined? And if not, can they do some dimension reduction, or do they have to go all the way to causal representation learning, which is interesting but challenging? And then whether they have time series or not, and whether that's stationary, and there might be some pre-processing that makes it stationary or not, and there's some frameworks for this. And then the question is, do they want to do causal discovery, or do they know the graph? If they know the graph, are they interested in total effects? If not, then likely, if they're not linear, you end up in counterfactuals. And if it's about total effects, a question here about data sets is, do you have multiple data sets from different distributions? If not, do you have hidden confounders? Maybe not. Is it linear? Maybe you end up with the path method or adjustment. If that's not identifiable by adjustment, you might end up with a front door or do calculus, or maybe up to instrumental variables. And that is my attempt to structure this. And I'm super happy to get feedback on this because it's, I think, fun to have such a graph that tries to give a user an idea of which types of methods can work.
Jacob, sorry, quick interruption.
Yeah.
There's a quick question. Can you also say something about the dimension of the system in this graphical scheme?
The dimension of the system. I don't get the question. Like maybe.
I guess maybe the question is about how large of a system you're trying to model, or if there are any restrictions on the size. That's my
So this is
interpretation.
not about any particular model, system, or Earth. This is just about trying to find the right method for the right scientific question. But maybe at the end I can get back to this better.
Thanks.
Yeah, so I'm happy to get feedback on this, of course. Then in this review paper, we also cover a little table of which methods are implemented in which packages. And I hope there's no errors, but maybe this is outdated already 2 years ago. Or I know there's efforts in PyY, and some packages are developed much further. But I try to do a little overview of which methods are implemented where, and some people want to use maybe Python, others want to use other methods, and so on. So there's always a good choice in these. And this brings me to the Tigramite Python package. So that's available on GitHub, also on pip. And it's under the GPL license, which I did years ago, and maybe I would do it different now, but it's too late. And Tigramite has different available tools. So one is about data processing and analysis, which I think it's important before you start causal inference to make a good choice of methodology. So there's methods to plot data, to plot joint densities, to plot these time-lagged functions, to get an idea of time lags. And then there's a large part of it dedicated to causal discovery. So you can learn causal graphs, and there's the methods we developed in my group. And there's a large range of independence tests for different types of data, different types of assumed relationships. And then there's causal effect estimation and mediation implemented. So this is based currently on optimal adjustment or any other adjustment set that you have. It uses scikit-learn to model dependencies, so it's non-parametric in that case. I also have a class for linear right-based causal effect and mediation estimation, and recently also a package or another class for a non-linear, non-additive causal mediation. And I get to this functionality in a bit. So purely on the coding structure, everything in Tigramite is framed around a data frame, and that handles a lot of the data issues that you have in time series data or general and real world data. And this is then imported or used or imported into the causal discovery algorithms, PCMCI, LPCMCI, and so on. And these also import particular conditional independence test classes. And the data frame also is used by the causal effect estimation mediation classes. Tigramite has a plotting module. I, at the time, was only looking into network X, and I didn't like the arrows, and I needed much more different types and colors of arrows. And so I coded this plotting module, which you have seen here in these plots. And there's dozens, maybe, I don't know, 15 tutorials or so that for each method, basically, to guide the user. So the main idea was to decouple data handling and analysis, the conditional independence tests, discovery algorithms, and effect estimation. And everything is trying to be modular, so inside these classes to reuse functionality and so on. And a simple usage example would be you have your data here as a NumPy array. You create a data frame of it. You also initialize this class PCMCI, for example, with a conditional independence test, for example, partial correlation. And then you run a method, PCMCI plus, with a certain time lag and PC alpha, that would be the kind of minimal parameters. You get results, and then you get the p-value matrix, but you also get, or test statistic, but you also get the graph, and then you can plot it with the Tigramite plotting package and get such a graph here. So going into a little bit more detail about the data frame object. So the initialization of this is firstly, of course, the data, and this may be an array of shape, time, and number of nodes, or it may be a shape with another dimension here when you have multiple environments. So it can then make use of multiple time series data sets or as a dictionary. And this leads to these two analysis modes of single or multiple data sets. You can also use a mask if you have samples that you don't want to use in a particular analysis, like summer and winter month is typical in climate science. You also have an array giving the data type. So it might give a different data type for even individual sample points. It's currently not much used, but why not in the future? So that differentiates continuous or discrete data. And then there's this functionality of which I call vector variables. And this means that maybe your underlying data frame contains hundreds of columns, but then your node you want to be defined just as the first two columns. So it's a two-dimensional underlying sample, underlying random variable. But the node here that you want to learn is just it's just one node, but it comprises basically two columns in your data frame. And in that way, you can very flexibly define these vector valued variables, and then that is digested by the dependence tests and other functionality. You can also specify the reference point. So this might be, I only want to use like summer or winter. That is part of masking maybe, but you can also specify only, half of the sample. Or this allows to basically also do bootstrapping by specifying like a random draw with replacement from the data. This is used in all the packages. There's a missing flag for missing samples and variable names. And then once that is initialized, every method, the causal discovery methods, they all make use of this construct array function of this class. And that converts any query into an array that is then digestible by conditional independence tests, by scikit-learn. Basically, it creates an array that contains the correct values x, y, and z, and maybe x, y, z are time-delayed samples, maybe some are missing because of masking, and all this stuff is handled by the construct array function so that the array that the method gets is without missing samples, and it's just kind of like the IID data that scikit-learn digests or NumPy digests and so on. And there's also modules for data transformations. Then there's the time series causal discovery algorithms class or classes. And this are, I mentioned PCMCI, PCMCI Plus, latent PCMCI, and I discussed them before. So this is a process graph now, and this is a time series graph with these bidirected edges. So that's for time series max. And the way these classes work is they are initialized with the data frame with a conditional independence test. And then you just use something like run jpcmci plus. You can put prior assumptions about your graph also as a parameter. So that might be this link must be there. This cannot be removed in the algorithm, or it might be that link is oriented that way if it exists. So it's a bit flexible in terms of adjacencies and orientations. Or you say that this link cannot be there. So your prior knowledge can be quite flexible. And there can be maximum time lag, of course, of this graph, and then an alpha level of the CI test. And I have a bootstrap functionality covering all these methods. So that's a separate function where you just call a method and its arguments. And then it runs a bootstrap of these methods. And we have one paper about this, because I think it's not so frequent that causal discovery comes with bootstraps, but there's some for the PC algorithm, and this is for the time series version in this case. The independence test that we have.
Jakob, sorry to interrupt. So there are two questions. The first one is, can it decide which method to use for which variable pairs depending on their linear relationships? And then the other one is the maximum lag. Is it estimable? Can it be estimated automatically or set by hand only?
Right. So far, I don't have like an automatic method recommendation system. That's my goal a bit in the future. But so far, it's the user would have to look into the assumptions and what are they willing to make, and then choose the method. And the maximum time lag, there I have in the tutorial a recommendation, like either physically, like in atmospheric science, that things decay after 2 months. So that's your physical maximum time lag. Or you can try to learn that or estimate it using these lagged functions, basically, at which point the lag functions here decay to almost 0. And that's assuming faithfulness, that's the maximum causal link you can get by far. It's a very conservative estimate. So those are my recommendations in the tutorial on this.
All right, thank you.
So the independence tests, they are currently implemented for really various assumptions, like univariate continuous data with linear dependencies and Gaussian noise, or robust parkour allows for different marginal distributions. Then this is weighted least square for heteroscedastic data. I have a Gaussian process distance correlation-based test for like additive nonlinear dependencies, also with a GPU version. I have this CMI KNN test that I developed for, almost arbitrary, but of course we know that no free lunch theorems exist. We have G squared, a symbolic, like a categorical conditional mutual information test. Regression CI uses regressions with and without the X in principle, and that can be applied to mixed data with like categorical and discrete data. This is of course categorical, and all these are more for continuous samples. And then we have a recent method, CMI KNN mixed, which is also for discrete and categorical data and general dependencies among the continuous variables. And some of these allow for analytic asymptotics, some just are based on permutation tests. And I also have a nice wrapper class that makes every univariate test multivariate, which is called pairwise multi-CI, and there's a paper also by a PhD student of mine. And now these tests, they all they have a wrapper class, a base class, and that gives rise to this run test, and that is based on some X, some Y, some Z, and also they might be multivariate here, even the X and the Y. And that then spits out p-values and test statistics. And so you can write your own CI test by subclassing and making use, for example, of the permutation test functionality that is used by these tests. Example is the CMI KNN, which is then initialized also with the KNN parameter significance. In that case, of course, there's no analytics, and there's mask types, which allows to, again, specify how to deal with a certain mask. And the permutation test is correct in the sense that it is a local permutation test. When you test for XY independent given Z, you of course only shuffle samples where the Z value is similar to make a asymptotically correct shuffle test here. Okay, moving to causal effect estimation. So here we have the causal effects class, and that is initialized with a graph. That's of course the assumption, and that graph type can be implemented now as DAGs, and they can be static DAGs or static ADMGs, or they can be these stationary DAGs or stationary ADMGs. Then you would specify your X and your Y and potentially a conditional effect variable if you want to estimate conditional causal effects. And based on that, you then have a fit function which uses the data frame and takes care of all those missing values and masks and whatnot. And you specify a scikit-learn estimator here. You specify your adjustment set, and that implemented is the optimal adjustment that was developed by Henkel for DAGs and by myself for ADMGs. Or you can just use your own. You can also specify like a conditional effect estimator for, in my case, this is nested effect estimation. And you can do prior transformations and the masking choice. And then you predict, and intervention can be then an array of interventions, so to get multiple predictions at once. And also they can be hard or soft. In this case, this is the way you compute these interventions. And also here I have this bootstrap functionality to use potentially block bootstraps of all the methodology that you see here. And there's a lot of other little functionality, for example, get all valid adjustment sets. And this is thanks to Van der Zander and Lischkewitz and Textor, because they have this nice package and pseudocode. And I just implemented this in Python here to, for example, run through all the valid adjustment sets. And there's this check optimality, which checks whether a given graph admits an optimal adjustment set. And maybe that's all jargon now. This optimal adjustment is something I may get to back in the end. It tries to find the optimal adjustment set in terms of asymptotic variance from among all valid adjustment sets. And this theory is asymptotically correct for linear SEMs, and for others, there's just numerics. But I think the optimal adjustment set is really working often better, also in nonlinear cases. So maybe just a plot of non-parametric causal effect estimation. So when you give it a time series graph, what internally is computed is a finite projection of a time series graph, which may look like this, and that's then containing these bidirected edges because of kind of the past. And you can then color your source node, your target node, and the mediators, and then these orange nodes would be the optimal adjustment set in that case. And then you can use, in this case, like a multi-layer perceptron to estimate some nice nonlinear causal effect and do some bootstrap uncertainty estimation. Okay, moving just quickly.
Jakob, can I interrupt again? Sorry. So there's a question about whether you have any recommendations on what method to choose for causal discovery and effect estimation when it comes to real-world observational health data where stationarity assumptions don't generally hold.
Ooh, yeah, big question. I mean, I think I cover this, like I cannot say that generally now, but I think this whole package gives a lot of guidance by, for example, here mentioning the assumptions, and if it's non-stationary, maybe you have to use, maybe either you can check which parts of the data are stationary, or you do sliding windows, or you use a more complex method that doesn't try to assume that. We are developing further methods currently. And similarly for effect estimation, a big topic, of course, how to define, but here it's, I mean, the graph you kind of put in, and if you don't know it, then you have to go back to causal discovery or use different graphs that you assume and then transparently lay out for this graph, you get this effect, for this graph, you get this effect. Of course, choosing the right scikit-learn method is up to, whether you want to assume linearity or not, and that can be tested, of course. So parts are, I discuss in the tutorials of Tigramite, and parts are just general things like, do you use KNN or linear regression? That's kind of covered in scikit-learn.
Thank you. And another quick question of, you mentioned that in causal discovery, you can accommodate like prior knowledge into the code, and whether there is also a way to incorporate like Bayesian approaches and specifying priors, etc.
So this is constraint-based, this whole framework here. And so the way you encode link assumptions is hard. You either say this link is there or not. If you want to do like Bayesian stuff, you have to go to Bayesian packages or use SAT solvers where you kind of specify, I believe this independence test with this confidence and so on. And then it's computationally more expensive, but can deal better with such prior uncertainties. But it's kind of hard here. Okay, continuing, there's the causal mediation class, and one that we have is for really non-parametric situations. Similarly to the graph, to the causal effects class, it allows a graph array, different types of graphs, and then you can fit natural direct or indirect effects, specify the estimators to deal with. So this is a complex class where you can define which nodes are continuous or categorical, and then find the correct estimation strategy. For purely linear systems, I have a much faster version, the linear mediation class. So this is all based on estimating path coefficients and using the right method here. And this has a lot of functionality about total effects, mediated effects, also bootstraps, and is much faster, of course, in a linear case. And finally, there's also a toy model and tutorials part of Tigramite. So the toy models, I think, are very useful for users to play around, maybe generate data where they know the causal structure, but that has some types of challenges, and then evaluate whether a certain method works good or not on the sample size you have. And that class digests like a links dictionary, which would be link or variable j is caused by variable I at lag tau with a coefficient and this types of functional dependency. So it's a generalized additive model. You can specify noise distributions. You can also generate interventional data where you just specify interventions and then also hard or soft interventions. There's also a function to just generate SCMs based on drawing coefficients from a range, drawing link densities. There's a lot of different parameters in that function. And that's maybe useful for method developers. And then there's a lot of tutorials in different folders. There's case studies, discovery, effect estimation, feature learning, and some data challenges. And this is also my preprint of that perspective paper on just the tutorials section. And there's lots of applications that I just put on the slide here for reference where these methods have been used, and I collaborated on these. And going back to this, which I try to make really as an important point for practitioners, to try to find the best method by just asking yourself, which assumptions am I willing to make about the underlying system? That's a task that partially can be tested on the data and partially cannot. So I don't know, something like, are there hidden confounders? There is some tests, of course, but usually it's something that you have to make as an assumption, and you will also then need to discuss this in a scientific publication. And this tries to make this transparent so you don't have implicit assumptions. I think given the time, I will not go through a tutorial here in depth, but there's, for example, the biogeoscience case study that goes all the way basically through this, how to use this flowchart and how to choose the right hyperparameters of a particular method. And coming to an end, the idea of Tigramite is to have extensibility, so it's easy to integrate further CI tests. And also many subroutines are parallelized via joblib. There's some script for MPI that I have for selected methods. And then there's, of course, NumPy is parallelized internally, so it's always a discussion to have whether it makes sense to parallelize outside if NumPy is internally doing this already. There's some GPU support for like some GPDC torch conditional independence tests. And any further algorithms would benefit much from the data frame handling of all the specifics about time series, where you need to shift lags and missing values and masking, and some are vector valued and so on. So this is really trying to handle this. My roadmap, there's lots of things that I want to do, and I'm happy for any pull requests on new functionality. So I'm trying to integrate further time series causal discovery methods, adding further CI tests. One branch that I'm looking into in my group is adding validation methods. So can we check assumption violations? Can we check finite sample uncertainty better, even though it's constraint-based? Then I want to expand causal effect estimation. For example, there's the ID algorithm, and I haven't integrated that yet. It's something on my list. Then do more counterfactual analysis, more estimators for conditional effects. Also, currently you can use it fine for a purely IID method. It's just your graph is just the contemporaneous slice of the time series graph. So all the methods are applicable to IID data. I want to expand the benchmark suite and also have what was asked now, more functionality to method and hyperparameter choice. And I mentioned this, some assumptions you have to make and lay out, and some can be tested on the data, like is it linear or nonlinear, maybe. And with that, I summarize, again, Tigramite as a causal inference for time series package, which I think has not been there before. It's modular and extensible. It's quite widely used. Currently, it's open source, of course, and I try to make this question assumptions data approach more popular also in this paper here. And with that, I'm happy to take questions and thank my group that contribute lots of methods and code. And yeah, thanks a lot for your attention.
Thank you, Jacob, for the tutorial. This looks like a wholesome package, and there are quite a few questions. So when you were talking about the what methods you choose for non-stationary data, so there was a follow-up to that. So if we apply fractional differentiation to the series to get them stationary enough, could that be a good solution? And something related to that, another person asked is, can your package process non-stationary time series automatically, or should the user process them before using your package?
Right. Yeah. Good question. So this differentiation prior analysis. So I'm really not in the economics literature so much, where this is common practice. In kind of the physical sciences, you wouldn't do it, because if you do fractional, like if you do differences of temperature, then your time series variable would be not temperature anymore, but it would be delta temperature. And that is a different interpretation. And your causal effects would be in terms of this, and in causal discovery would be in terms of this. So it's not so innocent to just take differences to make it stationary. In the end, you have a different causal variable, and that has different interpretations. And that is what you have to keep in mind. The other question about non-stationarity. So it was already in between. So right now, the methods, part of them assume stationarity, part of them don't. So going back here, PCMCI, all of these assume stationarity. This doesn't. It assumes that the system has a finite number of regimes between which it switches, and then it tries to learn those regimes. JPCMCI is kind of, if you have multiple data sets, and then of course there can be non-stationarity in space, but each single time series data set should be stationary. It's a very like you cannot just deal with arbitrary stationarity. That's just no free lunch. So you have to make assumptions about how non-stationarity it is. And if it's, for example, in different regimes, then go to this method. If it's maybe smoothly varying over time, maybe sliding windows help. If it's periodic, so like summer and winter, and you have prior knowledge about that, then you can mask your data to make the different masked subsets stationary. Yeah, I suggest to think about your system, maybe just plot the data and look whether you see strong trends and reason about where these trends come from. And maybe there's a climate change trend, and then you can subtract like a smoothed version of this data to remove that trend, assuming additivity and so on. And so it always requires you to put in thought about what is the reason for this non-stationarity, and then try to appropriately deal with it.
Great. So there's another question. Can you say more about the kinds of causal effects that are of interest in time series, especially like treatment regimes and differences in identification assumptions across them?
What was the first part of your sentence? Like discuss just
Say
causal
more.
effects?
Yeah, say more about what kind of causal effects are of interest in time series.
Yeah, good question. So what you see here is basically a graph that comes from a stationary time series graph, and you see here that you can, in the end, it's just a graph. It's the finite graph now. This is non-infinite, and this is finite, the projection of this. And in this graph, basically, might be typically an ADMG, and then all the results about identification hold. And in this package, I only implemented adjustment, so not ID. You can, however, for example, learn causal effects also for joint interventions. So you might specify that to be a whole passed array of axes that you want to intervene on. and also more than one target node. Of course, we know that this just decouples. And then, yeah, use the functionality of finding the optimal set for joint interventions or other adjustments for joint interventions. We know that most of these identification results also hold for joint interventions, which I make use of here. But for example, I didn't implement ID algorithm, or there's no front door, there's no instrumental variables implemented here. That's all stuff I want to work out further.
Is my understanding correct that for estimation, it's estimation of the adjustment functional basically at this stage, right?
Yeah, like this. Well, by using a certain sklearn method, you specify how you fit by which estimator, and by specifying either optimal and then it's automatically chosen, or your user-defined set, and then maybe it tells you no, not a valid set. There's a test for this, and so yeah, you can flexibly use different adjustment sets.
Great. So another question is about how do you recommend testing the effectiveness of the different time series-based causal discovery methods, given that the challenge is lack of ground truth in some applications?
Yeah. That's my kind of outlook. Adding validation method. It's a big topic, right? Like, so if you don't have ground truth, then what you can do in constraint-based, what I've implemented is these bootstrap repeated computations of causal discovery algorithms. So in the end, you get basically 1,000 graphs, and then you can do a majority vote and take that as your finite graph. Of course, there's challenges with that. It also gives you like how many of the bootstraps does this link exist, and so far this is just numerical. And I talked to Thomas Richardson once on a walk about what's the theory behind, like in what sense is this bootstrap-based relating to kind of uncertainty in a Bayesian sense or so. And so far it's really just more a method, and we have a lot of numerical evaluations, but that's one approach to do finite sample uncertainty estimation. And the other direction is to test whether the data generating process has assumption violations, and that's quite recent work where we look into faithfulness violations. Can we detect them, and can we detect whether they exist? And that might give rise to using other methods that are more robust against faithfulness violations. But it's a tricky topic, and it's interesting, and lots of research should go into this.
Okay, great. Another question is, could you use these methods for causal inference in any dynamical systems? For example, in lines of Peters and company's work, it's Peters, Bauer, and Pfister 2022. I'm not familiar with the paper, maybe you are.
Or what's the method kind of?
Yeah, can they be used for any dynamical systems, and the ones that have been talked about in Peters and company? Yeah.
Yeah, so it is used. I mean, the application target here is time series data, so that might come from a dynamical system. It goes to my nice flow chart. Entering causal discovery here, maybe it's just one data set. If you have a deterministic system, then there's these state space methods, convergent cross mapping, and that they are made for this target. Like, that we assume random variables, so you would not have deterministic variables. And yeah, I don't know the method that you mentioned, but maybe that's all I can say now. This tries to answer like which assumptions lead you to which type of method.
Okay. And are you currently exploring other conditional independent tests for higher order multivariate relationships?
Well, I mean, many of these independence tests are for multivariate relationships. So those are my independence tests. So, like for example, CMI is natively supporting multivariate X. You see that this is a list, and this can be just multi-variables.
Mhm.
And then CMI simp, the same, CMYK mixed, the same. G squared, I think also, no, it doesn't, I think not now, but actually that's not a big thing.
But I guess they specified like higher order, so maybe just like are they suitable for bigger dimensions?
Higher order, what do you mean by higher order? So CMI, of course, is KNN based, so it doesn't assume any polynomials or whatever, it's just KNN based. So that's in principle the most maybe a general way to make assumptions, and therefore the least power on dependencies that are linear or nicely behaved. I think I don't exactly know what you mean by this higher order now. Is it just dependency type of nonlinearity or another one?
I'm not sure if that's all that is said, so maybe whoever asked this question can clarify in a follow-up. Yeah.
Yeah.
Okay. So there's more questions about the stationarity. So there's one, rather than explicitly adjusting for assumed stationarity, is there support for automatically modeling a stationarity as a latent property?
Yeah, I have done that, or you can kind of always do that. And the way I did it is basically you can create your own variable. Maybe that's some kind of smooth oscillatory function over time. Like you basically add a variable s here and add some of your choice, and this is maybe your model of non-stationarity. And then you use your link assumptions to specify that all these variables are caused by that variable, and they're always caused by that in the link assumptions. And then the independence tests will condition on that variable. And if you run an independence test between like x1 and x2, conditioning on that constructed variable that models your non-stationarity, then you account for it, right? So that's a way to do that.
Okay.
And then your independence test can be CMI KNN, or it can be linear. And if it's linear and you put in as your maybe a dummy variable of like, yeah, a dummy variable, if you have kind of a piecewise constant values, then it's similar to running like a fixed effects regression in your partial correlation test. But it's maybe a bit too involved. But I think that's a way to deal with non-stationarity, by explicitly putting it in as another kind of artificial variable. There's something in my tutorial about this, in I don't know in which one, causal discovery. I think it's, yeah, I don't know.
All right, and the follow-up to that question, instead of higher order multivariates, and so say like synergistic multivariates. So there.
Yeah, that's a great question. We have one tutorial about synergy, but the way it's treated there is, if you know beforehand that, for example, two variables have a synergistic dependency towards another, then you basically specify them as a joint node. And then basically, instead of having three nodes here, you have your nodes would this, like basically that you form a new node covering both of these. And then you run causal discovery with a suitable independence test that deals with more vector valued or multivariate x, y, z. And then that is a way to deal with synergistic data. However, if you mean that, well, what if I just have x1, x2, x3, and I have really like dyadic relations where just, you have basically a faithfulness violation where it's just x1 and x2 jointly cause x3 and there's no marginal dependency. So this is a case of faithfulness violation, and that's why there is some methods in this direction but they're not implemented for the time series. I don't know. I'm not aware of time series methods that can deal with these types of synergistic faithfulness violations. There's always this argument against these types of faithfulness violations that it's a super fine-tuning of the SCM to really get zero marginal dependence. But of course, in finite samples, you can easily overlook such dependencies. We have a tutorial on basically a priori knowing synergistic relations and then using vectoral variables.
Thank you. And another question just popped up. So do you have time series data sets with ground truth causal discovery to play with?
I do. I should have put that in. I have this whole, it's not here. I have this whole benchmark platform called Causme, causme.net, and that features lots of synthetic, like largely synthetic data sets with different challenges of number of variables, time series length, linear, nonlinear, loads of other challenges, and also some real data data sets with known ground truth. Of course, the known is always with a grain of salt. There's this river runoff data, which was used in one of here. Like this is, for example, something where the river runoff was applied to. And also some hybrid where it's like highly realistic synthetic data, because you have these core climate models that are basically models, twins of the Earth, but yeah, still you can implement, or you know more about the causal structure. So causme.net has a lot of these. I don't have them in Tigramite, it's just separate. And I have to say that Causme is it is a benchmark, so it's not that you can download the ground truth. And some people ask me, and it's on my list to basically provide kind of validation data with ground truth for all these deep learning methods to learn on. But I want to keep it as a benchmark that this cannot be tricked.
Awesome. Thank you so much again for the tutorial and for taking the questions and the explanations. I think that's all we got, and I'll pass it to Dominic for the wrap up.
All right. Yeah. Thank you. Thank you again for the very nice tutorial. I will now quickly wrap up. I hope that's okay. So yeah, so next week, thank you all for coming today. Next week, we're gonna have a talk by Woo Suk Ha from the Korea Advanced Institute of Science and Technology, who will talk about domain adaptation, in particular, when few labeled target data suffice, a theory of semi-supervised domain adaptation via fine-tuning from multiple adaptive starts. Yeah, thank you all for coming. Thank you again, Jakob, and see you all next week.
Thanks.
Yeah.
Thanks a lot.